All right, I wanted to do a quick video on half-life and on doubling time, which is really the same idea here. So I just Googled some common half-lives, and I'll just use that as an example. The basic idea is that in the real world, sometimes things break down. Some substances, they don't stay the same over time, they break down over time. And on average, it takes a certain amount of time for it to break down so that there's half remaining. Okay, so let's just look at a example here. This one, Americium 241 has a half-life of 432.2 years. So the way I interpret that is that if I start with 100 grams, or if I start with 100 pounds or 100 whatever of Americium 241, then after 432.2 years have gone by, I'm going to have half as much. So the amount of time it takes for me to go from 100 to 50 is 432.2 years. The amount of time it takes for me to go from 50 to 25 is also 432.2 years. The amount of time it takes to go from 25 to 12.5 is also 432.2 years. Half-life is a chunk of time that it takes to decay by half. So I could take any of these substances and it would be the same concept, that the half-life is the lifetime, the lifespan for half of the substance. Okay? So let's look at one other example in that way. Let's look at this one. Copper 62, 9.74 minutes right there. That means if I have 100% of my original amount, it's going to take 9.72 minutes, 9.74 minutes to get to 50. And it's going to take another 9.74 minutes to get to 25, etc., etc., etc. So what you can do though is you can take this to come up with an equation that works for any specific time. So for example, let's say I wanted to look at this a little more specifically for my copper of 9.74 minutes. I know when x is equal to 0, I have 100. When x is equal to 9.74, I have 50 remaining. When I have two copies of the half-life, that's 9.74 times 2. 9.74 times 2 is 19.48, and that's when I have 25 remaining. I can use this and I can actually come up with an equation. The amount of copper at any time is 100, because that's what I started with, times 1 half, or I could use 0.5 if you like decimals, raised to the t over 9.74. The t right here stands for the time in minutes. So if I wanted to know, for example, how much it decays after 1 minute, I can just take my growth rate of 1 half and raise that to the 1 over 9.74. And this tells me that after 1 minute, that's how much is remaining. 93% is remaining. So it loses about 7% a minute. And after about 9.74 minutes, it's lost half of its original value. Similarly, for my americium, I could say the amount is 100 times 0.5 raised to the t over 432.2. But in this one, I have to be careful. This t is the time in years. That's the whole idea of half-life. The most common half-life that I see out there is carbon 14. And we can find that one on the table. Let's use blue for carbon 14. So carbon-14 is something that people use when they're trying to figure out how old something is. If they dig up a fossil, or if they dig up something from like archaeology, they want to know how long ago it happened, they'll use carbon-14. And it has a half-life of 5,730 years. So if I had a table looking like this, where I start with 100, and let's say I want to find a few values. Let's say I want to know how much is there after 100 years. I want to know when it reaches 50 and when it reaches 25. I can fill in some of those values. I can notice that 50 is half of 100, which means it's going to take one half-life to reach 50. It's going to take two half-lives, so I just go 5730 times 2, and that's 11460 to get to 25. It would just take three half-lives, 17190, just take three half-lives to get to 12.5, like that. To find the value after 100 years is a little trickier, but I can just use my equation where I started with 100 and I did 0.5 raised to the t over 5730. So to fill in the 100, I go 100, 0.5 raised to the 100 over 5730. And that's that value right there, 98.797798. So that's the basic idea of half-life. Half-life is the amount of time it takes to decay to half of your original amount. In each of these examples, I just started with 100 grams of the substance, but you could start, it depends on the problem you're doing, whatever your starting amount is the number that goes in front of the parentheses. The idea of doubling time is basically the same thing, but instead of it being a half that you're multiplying by, you're doubling. So for example, if you have, say, algae doubling every week, then let's say you start with doesn't matter, 3 square inches. Then I know that we're going to go, if we make an XY table, we're going to start with 3. When x is equal to 7, we're going to have 6. So I know that if I went 1, 2, 3, 4, 5, 6, that I'm going multiplying 1, 2, 3, 4, 5, 6, 7. I have 7 multiplications. 3 times something to the 7th power is 6. That means that something to the 7th power is doubling, and this means that I have 2 to the 1/7. The 7th root of 2 is my multiplier. In other words, just like my half-life problem, the amount of algae I have is 3 times 2 to the t over 7, right there. So half-life and doubling time are just two sides of the same coin, where they are the denominator of your exponent. Because when you make that your denominator, you control how long it takes before you multiply by that value. So I feel like you may still have some questions on half-life and on doubling time. So please ask questions. Let me know what I can do to help, and I'm happy to help explain.